Hey there, we're back with another Codeforces round. Looks like the site's kind of lagging. Hopefully we can load the problems. Standings. I don't think I've seen it be this bad in a while. Alright. Is this when we use M1? No, we're good. N rows, M columns. Second rows by DR rows and DC columns. Okay. Okay. Where's the illustration? Oh, come on. Is this a GIF? No. One, two, three, four, five, six, seven, 8, 9. I see. Okay, so I think you just simulate it, and then you are good. Otherwise, I think we need two separate. RB plus DR, RB plus equals DR, otherwise DR. I guess we want to do that. And regardless, this happens. CB plus DC. DC times 1. CB plus equals DC. Okay, that's it. Steps plus plus. I can't even submit. What? The minimal sites aren't even working? I don't know what's happened. Okay, pretest pass. I have no idea what's going on now. Okay, I see. Oh, wow, okay. Why is n up to 1,000? I kind of want to do cubic. Um, I think it's the one that never shows up again. It's 3, 6. It was 6, right? Or if you have like 5 and then you have 1, 2, 4, 5. I think it was 3. Is there an easier way to do this? I guess I could do it by doing deltas. Okay. Maybe there's something. Three, three, two, two, two. I'm just gonna submit because it's fine if I get a wrong answer on test one. Looks good. All right, time for C. D stands from ith to I minus 1th. 2D from I'm gonna maximize the smallest heap, okay. Okay. So just binary search the answer. Yeah, okay. Makes sense. This is a very standard idea. You need to go +1 if it's possible. I'm going to make a copy of H. Aside plus move, aside minus 1 plus equals move, aside. It's less than return false, otherwise return true here. And we're gonna run samples and see, I think we're good. Oh, we're not. What happened here? Am I misunderstanding what's here? Oh, you have to go from left to right? Oh, you have to go from left to right. What's up with that? Okay, the answer is still binary search, but now... This need is going to be... Well, it's kind of weird because... What about the one right behind us? I guess if we can... I see. So the problem we're running into is we can only get so much here. So if we want to satisfy the one right before us, then we're going to have to move 1x. We might have to move a bunch of extra behind us. Oh, okay. I think you just do this, but the amount that you can move is limited to... It's HI my skull, right? Because that's what it is. No? Oh, it's min SI my skull and HI. There we go. Okay. Oh, way behind on time here. Just 2 more problems? Okay. Oh, okay. Mm-hmm. That makes sense. Okay, that makes sense. Okay, so they both have some period. Okay. Okay, so I think this one is easier. And add cases, and let's just copy A. Actually, that's easier. All right, so okay, so after 2n moves, we should repeat, and after 2m moves, we should repeat. So after 2nm moves, the entire sequence repeats. And then it's just some math from there. Shouldn't be too bad. Yeah, n times m is not that big. Plus. Oh wow, that is an amazing warning. Amazing. Alright. So why don't I just all the time? What actually happened in the second example? Clean every second and still has the same probability. Oh, I didn't read P. That's the problem. everything is just off. Okay, got it. Okay, so it's a nice piece in. So at least just all right, and okay. Oh, that's what? I'm doing 8 steps. Oh yeah, it's like okay. Someone should have gotten it already. It's not that hard. Oh, what's wrong with me? Okay, so I feel like this is the right formula. Why is section 1 equals to 0? Oh. Great. Okay, now I can figure out what's going on here. I have no idea what the number is. 10, oh, that's huge. Steps then. Oh, no. It is actually. Is that right? All right, let's keep going. No more problem. I haven't made any wrong smiths, but I'm pretty far behind. All right, so we've got a tree. Got a binary tree. We can duplicate up to k, but it has to be. I've already solved this. Okay. I only did this problem. Okay, it took 28 minutes. Got it. Okay. Okay, so what we've got is okay, so you pick A and A. That's interesting. In general, would it be better to duplicate this character or not? If you just had a string, if you just duplicate everything individually, then Yeah, the question is just, is the next non-equal thing smaller or bigger? If it's bigger, you do duplicate. Now we have two more constraints. We have the k constraint, and we have, the k constraint we would just do first k times. Then we have the root path constraint. That's the only one that actually matters in a tree. Otherwise, you might as well not be a tree. So so a is less than r. Oh, and in order to get a, we have to do k. And y is less, sorry, c is less than y, but, oh, we just don't have enough? Yeah, we don't have enough. So do we just kind of do like a relatively simple greedy? Yeah, so here we're like, okay, we get to this a, and we're like, we do want to duplicate this a. And what do we have to do? Is there anything? Oh, it needs to be like, everything needs to be either done or it needs to be the left child every time. Okay, that's interesting. Yeah, if we had one more, we would do this a. If we had two more, we would do the c and the a. Yeah, that's fine. All right, so we're gonna do DFS. Void. So current size is gonna be equal to node. Current plus equals c node. Oh, no, this is not how you do it. All right, let's see how this looks. I didn't call this, so I'm gonna call this, and now we're gonna get it. So we have Bab, dark sign. Okay, great, and I mean, yeah, basically we can just do the greedy. Switching. So I'm going to go in order. I'm going to be like, okay, here's the node that I want to duplicate. Okay, Hino finished. Yeah. No, it's not too hard. Here's the node I want to duplicate. Can I do it? I can only do it if one, I can here's the node I want to duplicate. Only do it if number of nodes on the path from it up to the nearest duplicated node, the remaining of k, and all parents up to that point are right parents who are left children. Okay, so once you do that, you don't want to make it worse. Or there's something about that one that you can do. Either it makes it worse or there's not enough. So we can do this with jump pointers. Yeah, we totally could. Alright, so we're going to need to compute next different. Okay. Oh, this could just be string. Let's see, it's correct. All right. A BB. Yep. So what is it? Yeah, arc scion. Yeah, that makes sense. Okay. Okay, so now that we have this, do I want to use jump pointers? Is that the best way to do this? What is that? 2 minutes. It took me 2 minutes. Okay. It does feel like jump pointers would be the easiest way to do this. So let's do that. 18 is sufficient. That is going to be -2. All right. Or I don't actually need to keep that. But anyway, if or node equals children are 0. So we're the left child. What am I doing? Jump node k plus 1 equals jump node. Bad, otherwise it's jump node k. Okay. And that's it. So once you go any further, we get bad. And then also, we default to bad because, yeah, okay. All right, if next different, if current I is less than next different I, this is the node that we want to duplicate. And if jump xk is not bad, and either jump xk is anyone or done jump xk. How do we know if we should go to -1 or not? Wait, this is so weird. Oh, we need to find the last not done. Jump, so xk not done. X was jump xk not. So now we found the last. We found the last not done node, and now we're going to plus 1. Oh, if jump x0 is bad, 0. We can't jump to a bad. Up equals 0, continue, or if up is greater than k. So now we're going to simulate it. I'm going to change time to 50. Otherwise, we mark node up. And what do we print? print the resulting string. Okay. Don't need any of this stuff. Don't even need parent. Well, what happened here? Okay, that is a little bit weird. I should duplicate this first, and then I should duplicate this. Oh. Oh, I see. And not so I need to like I need to open settings. Okay, so duplicate is if we can jump, so we need the node to exist, and we need it to be not duplicated, and we need it to be all like right jumps. We know we're bad if we couldn't go up because of the wrong direction. So how does bad get generated? Yeah, bad gets generated from we do 1 1, we do 3 1. Here we do 2 2, then we do 6 2, then we do 5 1. Oh. Okay. No. That should be some now. I didn't do this, did I? I should do some double checking before I get a wrong answer. All right. We can actually, yeah, we can jump. It's bad, otherwise it's... Yep, that makes sense. Node from 0. for less than we want to do it. Just build the answer and then, yep. Okay, moved into 6th. A lot of people finishing right around this time. All right, I'll come back and explain solutions in a sec. Hey, all right, let's talk about these problems. And let's start from problem A. Now the site is working, so this GIF actually works, and it's pretty nice. Basically, yeah, you've got a robot. It does this kind of like diagonal movement, bouncing around, and you want to know the first time it'll be in the same row or column as the dirty cell. This one's pretty simple. N and M are only up to 100, so we can literally just simulate the process. Which is what I'm doing here. Main idea is if going toward the direction of DR or DC takes us out of the grid, then we flip the direction. And once we hit the same row or column, we just print out the number of steps we've taken. Commit here. So yeah, this one's pretty simple. So let's move on to B. Also a bunch more animations if you want to check those out. Problem B. Oh yeah, so problem B, you start with the range 1 through N, and every turn you pick one range, and Bob removes a number from the range, and it splits into 2 ranges, or up to 2 ranges after that. And then once it's empty, we know basically the set of all of the ranges that were created, and we want to know which range ended up getting broken down at which point. Main idea here is once you have a range, for example, let's say you take 3, 6, you can look at all the other ranges that are contained in that range. So in this instance, you have 3, 5, you have 4, 4, you have 4, 5, and that's it. And the thing that was removed is the only number that doesn't appear. So 3, 4, 5 all appear in this range. 4 appears here, 4, 5 appears here. So for 3, 6, 6 never appeared. So 6 is the number that got removed from 3, 6, and you can see that here. So then the question is how to do this efficiently. The way I did it was I did it in n² time. So basically, for each range, I look at all the other ranges that it contains, and what I want to do is kind of set all of the numbers within that range to true, but that would be n cubed. That's too slow. So what I did instead, and maybe this wasn't necessary, maybe I could have just done the n cubed. I don't know. It seems kind of borderline when it's 1000, because it'll be 1000 times 1000 divided by 2 times another 1000 divided by 2 maybe. Yeah, it would probably actually work. I don't like these constraints if it's just borderline like that. I think you should either make this like 400 or you should make it, 3000 and just make it fail. Make it unambiguous. I bet if we look at the runtimes people are getting on this problem. We'll see a bunch of variation there. We'll have to get out of the Python range first. Yeah, so a lot of fast solutions, but then occasionally, a slow solution, which I assume is going to be something n cubed. Yeah, same situation here. So yeah, I think n cubed can work, but I did n squared. Basically, the idea is instead of iterating over the whole range, what we can do is we can store a delta array and then increment the first part of the range and then decrement the end. So increment the start of the range, decrement the end of the range. And then what we do is we just go from left to right, we add up the deltas, and the value at a certain point is the sum of the deltas before that point. And then once we hit a value of 0, we know that's the thing that was erased, so we can output that. So yeah, that's n squared. You could probably even do better than n squared, but I didn't bother to think about that for this problem since n is so small. All right, let's look at C. Okay, so C, they made some problem statement changes, and these would have been helpful because I was confused by this when I was doing the problem, but especially the order. So basically, you're going to, I don't know why clicking this takes you to the top. You're going to go from the third heap to the nth heap, and you can choose a number of stones to move, and then it describes how you move them. Some of them go to the i-2th heap, and some of them go to the i-1th heap. And then you want to maximize the number of stones that are left in the smallest heap after the process. So in general, when you're maximizing a minimum or minimizing a maximum or either of those, it's a good idea to think about binary search, because now instead of having to deal with a bunch of different mins at a time, you can just say, oh, my goal is to make everything over a certain amount, or at least a certain amount. So that's what we do here. We throw binary search in, and once we have that set up, we have a goal we want to achieve. We want to make everything at least this goal. And then there's a key greedy idea, which is, even though you have to go from the third to the nth in order, the greedy actually operates backwards from the nth to the third. And the key idea is, for the last thing, we already know how much more than the goal it is, so we can just greedily take as much as possible without making it go under the goal, and then hand it over to its two neighbors. And we keep doing that, we keep going backwards. The key idea is that the amount that we can take from a pile, it's the minimum of the extra it has over the goal and the starting amount. Because when we're going from left to right, we're gonna run into it and do the operation when it's at its starting amount. So even if it's gonna end up with a lot extra, we can only move at most of the starting amount. And we're gonna move that divided by 3, and we just do the operation. If at any point we run into something less than goal, we return false, otherwise we return true. Yeah, so that's C. 2 more problems. Problem D. So problem D is just problem A, but you have a probability of cleaning when you're on the same row or column instead of a guarantee. And you want to compute the expected time that you'll finish, modulo 10 to the 9th plus 7. So here the key idea is that there's actually a period for the row and a period for the column. The row and column operate pretty much independently. The only thing that's not independent between the two is that if they both end up lining up with the dirty cell, you still only get one chance to clean it. So what that means is we can basically think about row and column independently, except for that setup. And for the row, the period, meaning the amount of time it takes to repeat to exactly the same situation, is 2 times n-1. And for the column, it's 2 times m-1. So what that means is overall, if we do the LCM of those two, then we can treat that as the period of the whole thing. The LCM of 2n-1 and 2 times n-1 and 2 times n-1 is definitely a factor of this number. It could be smaller, but this number is definitely divisible by both of those two. So that's what I use here. And then, yeah, basically just simulate the process, same code from part A, problem A. But now we need to do a bit of probability stuff. This is basically solving a geometric series or kind of a recurrence relation on the expected time itself. This just takes a bit of math to set up, but once you do that, you know which steps you can clean on, you know the probability that you'll get it. Probability is, this value is actually tracking the probability that we haven't cleaned it up until this point. And yeah, this is just the math for the geometric series. You can kind of work that out on paper. Basically, this is the point where section is like the kind of the expected amount of time multiplied to complete it in this number of steps, multiplied by sort of the probability that it happens. This is the probability that we actually finish within sim steps. And yeah, just a bit of math to work this out, but it ends up working out nicely. And then, yeah, since n times m is bounded in the problem, this is fine in terms of the complexity. Yeah, so that's problem D. And then lastly, problem E. Yeah, so problem E, the main idea is that once we can build the string, right? And in general, in a string, you would want to duplicate a character if, let's say you have a string like this. The question is, should we duplicate the A if we can? Does that make the string better? The answer is yes, it does. Because AABDC is less than ABDC. And the reason it's better, if we kind of dig into it, is that A is smaller than the character after it, B. So in particular, AA is better than AB. And even if you had AAABDC and you were looking at, should I duplicate this A? The answer is still yes, because you would end up with AAAAB. And so it's really, the question is just, is this character less than the next character that's different? So for example, for the D here, we don't want to duplicate it because DD is worse than DC. And then the same thing for the C. We kind of assume that there's like an implicit negative infinity character afterward. So C is not less than negative infinity, so we don't want to duplicate it. So that kind of tells us what we should duplicate. Now we have this these additional constraints around doing it on the tree and having k total that we are allowed to duplicate. The way we handle that is we can still do the same greedy, where we want to duplicate the best ones from left to right in the string. And now the main idea is, okay, let's say we have an opportunity, or we have a character we know we would like to duplicate. So for example, the A in this string, we don't want to do the D. The question is, can we do it? And if we look at this, well, we have this A, we would have to do this K as well. And here it turns out that is fine, and we do want to do that. So we do duplicate both the A and the K. This is okay because we have at least 2 duplications. And the other thing that's important here is that 1 is to the right of 2 here. The K is to the right of the A. Because otherwise, in this case, this A, we don't want to duplicate this A because that would require duplicating this D. And as we saw earlier, duplicating the D is bad. So basically it comes down to, okay, I want to duplicate my current character. We're going to go do that in order of where they appear in the output string. And now there's a couple conditions that we need when we want to duplicate a character. First of all, we need to be able to go up to the root without exceeding the K limit that we have. And then second of all, we want to make sure that none of our parents of the nodes that we're duplicating are to the right of us, or to the left of us, sorry. So we want to make sure we're always going up and to the right. And we can just implement this in n squared pretty easily, but we need to optimize it because of the constraints. And so what we end up doing, in my case, I ended up doing jump pointers. So I compute the 2 to the kth ancestor at each point. But if at some point you have to go left, I don't allow that. And so I set that to a constant called bad. And now what we need to do, what we can do is pretty simple. It's just for each character, we know which node it is, and we can binary search using the jump pointers for how far we have to go up before we run into something that has already been duplicated, or we run into the root. And if we run into a parent that is on the left, then we know that it's bad. So that tells us how far up we can go, and then we just simply go up the tree and mark that many nodes as duplicated. So it's a greedy idea, and then at the end we just build the string again with the potential duplications. I guess I could have done this without another DFS, because I could just use the locations array in this case. But anyway, that's the main idea. So it's a greedy idea with a couple optimizations in order to get it fast enough. The main idea in my case was jump pointers. But yeah, that's it for this round. Ended up in 6th place pending system tests. So kind of like an average performance, I would say. Maybe slightly below average, I don't know. That seems probably about average, I'm not sure. Anyway, cool, so that's it for this contest. Yeah, I'll see you in the next video.